Okay, so this is the missing piece in probability, at least one of the big ones that we haven't talked about. We've mentioned this. We've actually did this in Algebra 2, if you remember it, but we're going to bring it back here and also learn a shortcut we did not learn in Algebra 2 to do this quickly and efficiently if you recognize it as binomial. So today's binomial. I think the next days can be geometric. So mostly binomial today. Here's your homework, so you can pause it if you have a question and you need to look at that. Okay. So what is binomial? So we have a little acronym here. It's called BINS. The four conditions for binomial are: first, it has to be binary. Bi means like bicycle has two tires. Possible when you have an event where there are only two outcomes, success and failure. Now we use that liberally. What I mean is, like, some events are obvious. Heads and tails when you flip a coin. That's success and failure. If you're trying to roll a 4 when you roll a die, you could consider that binomial, right? Rolling a 4, success. Not rolling a 4, failure. Chance of success, 1/6. Chance of failure, 5/6. So that would be okay to be binary. So there's only two outcomes, success and failure. Second thing, it has to be independent. We talked a lot about independence this year. Trials have to be independent of each other. Knowing the outcome of one trial doesn't help us, with the outcome of the second trial. They're just independent events. The number, it has to be a set number, a fixed number of trials. That's where geometric is a little bit different. But for binomial, it has to be a fixed number. You're trying to hit the target 3 out of 5 times. That's like you're going to shoot 5 times no matter what, and you're hoping to hit 3 of them. The same probability of success. So the probability of success cannot change. So it has to be the same probability of success from roll to roll, from flip to flip, whatever it is you're doing. It has to be the same probability of success. It can't change. So if you were grabbing cards out of a deck and keeping them, not putting them back, that's not going to be the same probability, because every time you grab a card, the probability is going to change for the next card. So that'd be an example of not binomial. Okay, so X is the possible values of X are 0, 1, 2. So we collect two numbers, two big numbers here, which is the number of trials is N. So if I'm shooting at the target 5 times, N would be 5. The probability of success, if I have an 80% chance of hitting the target, then P would be 0.8. This probability of success, not failure, is P. Okay, so is this binomial or not? Let's kind of think through the bins here. So genetics say that genes children receive from their birth parents are independent from one child to another. Each child of a particular set of birth parents has a probability of 0.25 of having type O blood. Suppose the parents have 5 children. Let X equal the number of children with type O blood. So check the bins. So is this binomial? So it looks like success is having type O blood. Failure is not having type O blood. I know there's other types of blood other than type O, more than just one, but not type O blood is failure, right? So it's binary as far as the B part. I is independent. It explicitly says they're independent, each birth here, so that's independent. A set number of trials. Okay, so they're having 5 children no matter what, so that's set. Okay. And then same probability of success. Every time they have a kid, it's a 0.25 chance for this particular couple. I don't know if that's always true, but evidently for this couple, that's true. And so that would be, it does. So it seems to pass all the tests there. Same probability, 0.25. Notice for the last two, those are variables, right? The set number is 5, so N is 5. And the set probability of success is 0.25, so P is 0.25. This is a binomial setting. And again, if you're defining a binomial setting, you want to define two things. What is N and what is P? Like, that's just important to start doing. You kind of think that way after a while. It's easy to do after a while. Start with a well-shuffled deck of 52 playing cards. Imagine you turn over the first 10 cards one at a time. Y is the number of aces you observe. Check the bins. So binary. So outcome, getting an ace, success, not getting an ace, failure. Passes the first check. Independent events. Does the probability, what if I turn over ace for the first card? Is there a different probability now since there's only 3 aces left instead of 4? Yeah, so it's not going to pass the test for independence there. It does have same number of trials or 10 cards, but we don't really have to keep checking at that point. And I don't think you have to prove it there. You can just say it a different way there, but they actually figured out the probability of that. Start with a well-shuffled deck of 52 cards. You turn over the top card, look at it, put the card back in the deck, and shuffle again. Oh, so now we have replacement. Okay, that's different. Repeat this process until you get an ace. W is the number of cards you had to turn over. So is this binary? So again, we talked about, so ace, success, not ace. So it passes that test. Independent events, because of the replacement, I think it passes that. Is it the same number of trials? Uh-oh. Repeat the process until you get an ace. Well, how many times is it going to take? I don't think it's the same number of trials, right? We don't know what's going on there. So that could be geometric maybe, but definitely not binomial. And so this is not a binomial setting. It has to pass to all 4 to be binomial. It's geometric. We'll learn about that later. Okay, here is the formula. I believe this is on your formula sheet here. And just a side note here. So when it says n over x there, so that notation. So when it says this, n over x, like that actually means, if you remember NCR, so NCX, sometimes I even call XR just because of the way the command, that's a command in your calculator. We'll get to that in a minute. It's how do you get there? You go to, I guess it's menu probability. That's called a combination, NCR. And so you would put the n comma x, whatever those numbers are, if you're doing that. So that's the first part of the formula there. I don't think you have to memorize this, the right-hand part here. So this is not actually the binomial theorem. This is saying, how do you actually calculate NCR? Well, the calculator does it for us, but that's the technical way of doing that. By the way, a factorial you should know how to do, which is 3 factorial means 3 times 2 times 1. 4 factorial would be 4 times 3 times 2 times 1, etc. 0 factorial, weirdly, is 1. So that's just a side note there. I don't think you have to know the formula on the right there. You have to know that n over x there means NCR. I think that's how you have to know. Okay, so the binomial, they said this. The binomial coefficient 5, 2 is not related to fraction 5 over 2. This is 5 choose 2, so we read it that way, and it's NCR. And so you would type in your calculator 5, comma 2 here, and it'll do it for you. It'll give you 10 different ways of doing that. So again, we know how to do that. It gives you the answer. Okay, finally we get to the binomial probability formula, the binomial theorem we call this. And so that's the formula. It is on your formula sheet, and you will use this, although you won't have to use it every time. You want to be able to use it for multiple choice questions, because sometimes they'll put the answer in that form. Instead of actually working it out, type it in their calculator, they just put it like that with numbers plugged in, basically. Reminding you that, but you don't need to know that. You need to know the NCR part there, because even when it's written out, it'll be written out more like that on a multiple choice question. I don't think they'll ever use that notation that I can think of. That is on the formula sheet. Okay. So introduce a stats class to binomial distributions. Mr. Desai does the pop quiz activity, in which each student in the class guesses an answer A through E on each of 10 multiple choice questions. Determine the correct answer for each, so the A, B, C, D are equally likely to be chosen. We're interested in the probability that the student gets exactly 4 correct answers on the pop quiz. You want to get exactly 4 right. What's the chance of that happening? Define a random variable interest, state its probability distribution, and identify the values of interest. So what is n and what is x there basically? So, or p, I guess we would need to know. So is it binomial, first of all? So is this binomial? Let's see. So there's one correct answer. There's 4 incorrect answers. So success or failure, correct or incorrect, that seems good. Each question seems independent of the previous one. There's exactly 10 questions. There's a set number of trials, so n is 10. The probability of success here would be 1 out of 5. There's 5 answer choices. They're all equally likely. So P is 1/5. So it is, X is the number of correct answers. So you want to say that in words there. So X is the number of correct answers a student gets on a pop quiz. We're counting that, right? We want to get 4 correct answers out of 10. So that's what we're counting there. X is a binomial random variable with n equals 10 and P is 1/5. We just mentioned that. And so we want to find the probability that X equals 4. And so that's the notation we like to use for binomials there. And you'll see that probability X equals 4. We want to get 4 wins out of 10 there, basically. Determine the correct answer was equally likely to be chosen. Determine the probability. So what are we going to do there? So if you go back to the theorem here, so you're gonna take that theorem and go, okay, let's kind of use the theorem. I have to get it so I can see it here. Get off that page. Okay, so we're going to use the theorem to kind of do this. So we know, I like to write this down. So n equals 10, I believe, and p was equal to 1/5. Okay, so, and we want to get probability of X equals 4, right? We want that. So this would be n is 10 over 4. Of course, the cool way to write that is really 10 choose 4. That's what we would type in our calculator, if that makes sense. That would be a combination times p, which is 1/5, to the x, which is 4, times 1 minus, kind of the complement there, 1 minus, not p, 1 minus 1/5, or 4/5. And it'd be fine to write 4/5 there. In fact, I usually do. I would write 1/5 to the 4th, and I just kind of calculate that. It's not too hard to do in your head, so I do it like that. And then n minus x would be 10 minus 4, or you could just say 6th power, right? And so either one of those are correct. They're both different, they're saying the same exact thing. One's just a little bit more simplified or clear. So this is what I would type in my calculator, essentially. So if we do that, we should get the right answer. Let's see. So by the way, on the Inspire, if you want to go NCR parentheses 10, 4, if you want to type it, literally type it, you can do it that way, times 1/5 to the power of 4 times 4/5 to the power of 6. We should get the right answer. I guess that's it. If you hit Control Divide, so 0.0, there's a 8.8% chance of this happening, it looks like. So let's see if they did the same answer. So they plugged into the formula and they got 8.8%, right? So they did the same thing. They wrote it out individually like that. I don't think you have to do that. I would type it all in the calculator all in one fell swoop like we did, and you'll get it. The probability is 8.8% that you get exactly 4 right on the quiz. Be sure to answer the question that was asked. So define the random, perform the calculations, show your work. We want to see that work, right? So N is one of the students in Mr. Tsai's class. Find the probability that a student would get 4 or more. Oh, no, this is a tougher question, right? So 4 or more. So if you're writing this out, this would be something like same N, right? So N is still 10, P is still 1/5. That's still true. But now we want the probability that X is 4 or more, so I think it includes 4. So essentially, we're saying there for the x value, we're kind of saying x is equal to 4 or 5 or 6 or 7 or 8 or 9 or 10. Does it make sense? So we would have to do the binomial theorem 1, 2, 3, 4, 5, 6, 7 times, oh my goodness, and add up all those answers. That's one way of doing it, and you can do it that way. The other way of doing it is to use the complement. I'm guessing they're going to do this. So you could do, this is equal to 1 minus the probability that x is less than 4, not including 4, by the way, but so that would be x is 3, 2, 1, or 0. So if you do it that way, to get this, you would be adding up x equals 0, 1, 2, and 3, which seems easier to me than maybe doing it this way, where you add up 7 terms, you do binomial theorem 7 times, now you only have to do the binomial theorem 4 times. So let's see what the way they did it, see if they used the complement. Again, same things there. Oh, they did. So then the pain is you've got to do the binomial theorem 4 times. Oh my goodness. So you do it first with 0 plugged in, then 1, then 2, then 3, and you evaluate all those things. So it's just a lot of work there. I think 0, 10, 1, 9, 2. They made a mistake there. Right above the third term there, it should be an 8. 2 and 8 have to add up to, anyway, the exponent should be 8 on that second to last 0.8 there. They made a mistake when they were writing that out. Okay, so that's one way of doing it. I want you to understand how that works, and you definitely want to be able to do that by hand, but there is a cooler way to do this. There's a shortcut. So let's go back to, first I'm going to go back to the first question. Let's answer this one. So remember this one, the probability of getting exactly 4. So we did it by hand, or we did the binomial theorem. There's actually a calculator command I never told you about in Algebra 2. It's pretty cool. So what you do is you go to menu. I'm guessing it's probability. Let's see, distributions maybe? I see it down there at the bottom for binomial PDF. When you want exactly 4 out of 10, so there's one value for doing the binomial theorem once, you go PDF. So you go PDF, you go N, oh, this is great. So N is 10, P is 0.5 or 1/5, right? Or 0.2, I guess, 0.2 or 1/5, I think it was. Yeah, 1 out of 5 answers. And then X is 4. I'm just so excited about the command, I'm losing my mind here. So this is really fun. Okay, so then you do this and you press enter. So again, that's number of trials, probably success. So if you're writing this out, just like we have in the past, you want to say something like binomial. This is what your work would look like, binomial PDF. You might put the numbers 10, 1/5, 4, and then put I think it would be fine to put either the words that you were asked to do that, or you could put N, P, and X there. Or again, the words, if you want to look back at this menu, probability, distributions, A is that. You could put number of trials there for the first one. You could put probability of success for the second one and the X value or something like that. Whatever the calculator tells you for those, you could also do it that way. Notice we got the same answer at 0.088. Okay, so now let's do this other one. Okay, so this is really cool. It saves a lot of time. So that saves a little bit of time, maybe. I mean, using binomial theorem once isn't that bad. But man, the other way, this way, oh, this is a monster, right? I mean, to work that out, I guess I got 12%. Wouldn't it be great if there was a way to do that in the calculator? Well, there is. So you go binomial, so menu 5, I think it's 5 distributions. If you scroll down or scroll up, either way, you'll see binomial CDF, kind of like norm CDF. Norm CDF is from a lower bound to an upper bound. Well, that's what binomial CDF does. Oh, this is great. Okay, so we go 10, Probability of success is 1 out of 5. Lower bound was 4. Upper bound is 10. Remember we want greater than x to be greater than or equal to 4. So 10 is the most it can be, so it would be 10 there. But 4 is okay, and it should give you the answer. Oh, that's beautiful. 12.087 or 0.1209. So it does do everything for us there. I want you to understand the other way, because sometimes the multiple choice questions ask that. Because the probability of getting 4 or more answers alone is only 12%, which is not small, Hannah should not be surprised by her quiz result of that. So now they're telling you about how to do that. Don't rely on calculator speak. Make sure to put the inputs. And they said it was okay to put the values there. 10 is n, p is 0.2, or trials. They put trials instead of n, but I think n would be okay as well. Draw a 3 and get it free. Oh, I like this. After lunch, after each customer orders, a touch screen displays a message. Press here to win a free lunch. Although it's electronic, I don't know if I trust that. Might be. A computer program that simulates one card being drawn from a standard deck. If the chosen card is a 3, the customer gets the order free. Otherwise, the customer has to pay the bill. So 4 out of 52, 1 out of 13 chance. That's not bad. I mean, for a free meal. Okay. On the first day, 250 customers placed lunch orders. Find the probability that exactly 10 of the 250 customers win a free lunch. So this seems like binomial. Is it PDF or CDF? Is there a lower bound and upper bound, or is there just one value there? And is it binomial? We have to think about that. So let's see. So are there just 2 outcomes? Get a 3 or not a 3? Probability of success, 1 out of 13 or 4 out of 52. Independent, they do seem independent. You're picking it, from a deck of 52 cards electronically, I think. And then is it same probability of success? Yeah, that seems to change a set number of trials. So it does seem binomial. So you could do it a couple different ways here, right? So you could, if you're working on this, you could say, let me just get that out of the way. Okay. So you could say, I like to label the variables. So n is 250, I guess. Let's see, probability of success is 1 out of 13, or you could write 4 out of 52. And then x, the number you want, x seems to be 10. We want to get exactly 10. So you could use the NCR, so it would be, so 250, choose 10, I believe. Okay, and then times probability of success, which is 1/13, to the, I might have to look back at this one. So what's the formula again? Sorry. I know it after a while. Probability of success to the x power, and then to the n minus x power in 1 minus p. Okay, so let's go back to this. So this would be to the x power, which is 10. And then this would be the 12/13 to the n250 minus 10 power. Wow, it's going to be weird. Okay, so you cut that in your calculator. Again, I think let's just do it just to make sure we get the right answer here. So binomial CDF or PDF. No, I'm just going to do NCR, right? So menu, 5 probability combinations. So we're going to do 250, comma 10. Hopefully I'm doing this right. Times parentheses 1/13 to the power of 10 times 12/13 to the power of 250 minus 10. Oh wow. Oh. One-13th? Yeah. Okay, hopefully that's right. 0.007, so 0.7%. Okay, let's see if that's the right answer. And then we'll do it another way as well. Oh, I didn't read this correctly. It's fewer than 10. Oh my goodness, we're not doing that one by hand. Fewer than 10. It helps to read carefully. Was that the first question? It was. I just didn't read the question. Sorry, guys. So I figured out 10. You would actually have to figure out, right, x is 9, 8, 7, 6, 5, 4, 3, 2, 1, and 0. So that'd be 10 different numbers to plug in. Oh my goodness, I'm not doing that by hand. I'm going to do binomial CDF, right? So menu 55 B on a CDF. So probability of success was, let's just see if we can see this. So 1 out of 13. And its number of trials, 250. Probability of success is 1 out of 13. Lower bound is 0. Upper bound, do we want to include 10? Fewer than 10, so just 9. So it should be 0.006. Okay, that's a different answer. Let's see if they did it the same way we did. I mean, you would have to perform the binomial theorem 10 times with all those different answers. That's too much work. So instead we do the binomial theorem like I did, by binomial CDF, I mean, and do it that way. In fact, only 9 customers want a free lunch. Does this give convincing evidence that the computer program is flawed? Okay, so there's a 6% chance, 0.6% chance of that happening. Oh, 0.6 is pretty low. That's, so what's they say? So because only 9 customers want a free lunch, we have convincing evidence the computer program is flawed. I wasn't trusting the computer program to begin with. It just, they could rig that. So I'd rather just, pick a card from a deck. That'd be great. Okay, and so now you can answer a few more questions here if you want extra practice. So are these binomial or not? So A, because there's no fixed number of trials, it's not. B, this is a binomial setting. These are good to practice with. And C is also a binomial setting. It's a game called Treasure Hunt. Players must select 5 numbers. They win a prize if at least 2 numbers match the numbers that are randomly selected by that lottery. Probability of winning is a prize is 0.183. We are interested in the probability the player wins a prize on exactly 2 of the next 7 days if they play the game once per day. Define the random variable of interest that state its probability distribution and identify the values of interest. Okay, so what is the variable of interest in words, right? So X is what? What are we kind of counting here? Do you win a prize, right? In the lottery. So X is that chance of that doing that. State is probability distribution. So what is N and what is P here? So want to win exactly 2 of the next 7 days. So N is 7. And the probability of success is 0.183. And then we want to get exactly 2. So probability that X equals 2. X is the number of prizes a player wins over the next 7 days. So I didn't specify that, so that would be helpful. You're kind of parroting back the question a little bit there. Part B, I guess I gave the answer for that as well. Determine the player wins a prize exactly 2 of the next 7 days. Because it's just one value there, it's fine to just do, binomial theorem. You also could have, if you wanted to, do menu 55A. And so number of trials is 7. Hit tab, probability of success is 0.183. And we want to win exactly twice. And that should give you the same answer. Again, if you do it that way, you need to tell what those calculator inputs are. Explain, and its number of trials, etc. If a player plays this game once daily for the next 7 days, what is probably will win fewer than 2 prizes? So fewer than 2 means 1 or 0. So you're plugging in X as 1 or 0 there. You're doing it twice. And you would add up those, or you do, right? The other option would be to get out the calculator and go, okay, menu 5, 5, and then B is CDF. And so Ennis number of trials is 7.183, whoops, 0.183. And lower bound would be 0, upper bound would be 1 there. And that should, yeah, that works. Should get it as well. So the shortcut, never taught you that in Algebra 2, but it's super nice. Okay, kind of a long screencast, but there you go. That's a missing piece. And the only thing we have left in this chapter for probability, to finish out probability, it's very exciting, is geometric. So we'll do that next time.